Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is velocity time graphs and acceleration time graphs. So far, if you just want to get an idea of where we're at in the kinematics unit, we've learned about position and what happens when the position changes. That is a displacement, a delta in position, a delta d. We've learned about average velocity and instantaneous velocity, and we've learned about acceleration. And so far, we've taken these ideas and looked at how they can be used in a graph to help represent motion, because sometimes a graph is an easier way to view motion than just by looking at symbols and equations. Well, today what we're going to do is take the remaining two symbols and see how they can be incorporated into a graph called a velocity time graph and then an acceleration time graph. And I think you're going to see that once we know how to graph these, we get more tools, we end up with more tools that can help us explain motion. So for now, just pause this video, take a look at the screen here to see where we are in the unit schedule, what the learning goals and success criteria are, and also the questions we're going to be answering today. Pause now. Okay, and you're back, and we are going to get started. So to get us started, I'd like you to consider these two graphs which come out of your textbook. It's Physics 11 by Addison Wesley. We're going to look at a very simple situation, some constant velocity motion. So figure 1.31 here shows the position time graph for a lion moving with constant velocity. Now yes, I am talking about position graphs at the moment because you're familiar with these. You know that when an object moves with a constant velocity, its position graph is a straight line. The straight line would be going up like this if the object is moving away from the origin, and it could be going down if the object was moving toward the origin. So you also know from our previous studies that if you measure the slope of this line, that will tell you the velocity of the object. So suppose you did have a lion that was moving. After 1 second it went 15 meters, after 2 seconds it was at the 30-meter mark, and so on. What would be the slope of this line? Well, since it's a straight line, we can just pick any 2 points like 0, 0, and this looks like about 75,5. The rise over the run looks like 75 meters east divided by a run of 5 seconds, and that of course is 15 meters per second east. And it's constant. So what we see next is the corresponding velocity graph. Now let's have a look at this. It has the same 5 seconds of time that the position graph had. However, instead of plotting positions, it's plotting velocity numbers. The 15 up here is the number that we calculated here. And because the velocity is constant, therefore we have to show a steady 15, and that is what this graph shows. So this is a very simple velocity time graph for constant velocity motion. There's really not much to it. There's nothing very difficult to understand here. There are some other interesting things that we can get from this graph, however. For example, if I told you that the lion was moving at a constant 15 meters per second for 5 seconds, and I asked you how far did it go, well, you would say, okay, well, 15 meters per second to the east times 5 seconds, that's 75 meters east. Very easy. Well, I'd like to show you something on the velocity graph that's kind of convenient. If you take a look at the area represented between the velocity graph and the time axis, you see it's rectangular. And the area of a rectangle is just length times width. Well, let's see what the length and the width are here. The length, the long side here, is 5, but that's 5 seconds. It's not a length as in meters, the way you would measure, let's say, a piece of wood if you were building something. It's a length in a kind of mathematical way that would be 5 seconds. So maybe we'd write 5 seconds. And the width here looks like it's 15, but not meters. It would be meters per second. So 15 meters per second. And of course that is east, so we have to put that in. I'm not talking about area like area in square meters for building something. I'm talking just area of a shape on a graph. Anyway, multiply these two out. What do you get? Of course, it's 75 meters. The seconds cancels, and you get this. This number is the same as what you calculated down here. So one of the nice things about the velocity time graph is that not only does it tell you about velocity, but if you calculate its area, then you get the displacement. So that's a rule for these kinds of graphs. On a VT graph, the area represents displacement. I'd also like to point out something that may not be obvious to you right off the bat, but soon you're going to see you're using this all the time. Looking at this graph, there's another thing we could calculate. If you think back to position graphs, we often calculated the slope, and it meant velocity. Well, on this graph, the slope is horizontal and therefore is 0. We don't really need to do a calculation here. A horizontal line has a 0 slope. So I'll write that in there. What in this kind of motion is equal to 0? What, if anything, is equal to 0? Can you figure out what it is? Pause the video and think about it for a moment. What in this lion's motion here is 0? Okay, and you're back after thinking about that. Well, if you're moving at a constant velocity, then that means the acceleration is 0. Constant velocity means no acceleration, and therefore the slope and the acceleration number are the same. Just like the area and the displacement numbers were the same, the slope and the acceleration are the same here. Therefore, we've learned another thing about VT graphs. The slope on such a graph is equal to the acceleration. Okay? So keep these things in mind. They are very important. We're going to be using them a lot. The slope and the area idea. And that, by the way, is the fact of the day. So, sorry, but jumping around there for a bit. This right here is the fact of the day. You can take that to class for tomorrow. We are going to have a quick quiz on that, and if you can tell me these two rules, then you will get perfect mark on tomorrow's quiz. All right. At this point, I'd like to jump away from my my sketch pad here and take you somewhere that we've been before. This is the PhET website, the interactive simulations. Go under physics, click on motion, and then go to Moving Man, which I believe I've shown you before. I already have it downloaded, so I'm just going to jump to it. Here it is. This is what's going to happen when you open it up. Now, what I'd like you to do, make sure you've clicked on charts at the top here. Get rid of the acceleration by just doing this, and leave yourself with position and velocity. This is, of course, the kind of graphs that we are talking about here, position and velocity graphs. Now, what I'd like you to do is click Show Vector, so we're going to get to see the velocity vector, and go up to the man here. When you click on him, the timer is going to start going. So what I want you to do is try to simulate the motion that we showed here. Constant velocity away from the origin. Let's see if we get a straight line position graph and a flat velocity graph. So ready? This is not easy, by the way, because it's hard to drag your finger across the mouse pad at a steady rate, but I'm going to give it a try. Here I go. Okay. Pause the video now and let's see whether I have, whether I've accomplished what I wanted. It would be nice if I could zoom out a little bit, because it's kind of hard to see what's going on here. Unfortunately, I can't. So here's what I'm going to do. I'm just going to clear this, start one more time, get this guy back to 0, and go a little bit slower. Okay, here we go. 3, 2, 1. Okay, how did I do? Well, if you look at the velocity graph here, sure enough, there's a roughly straight line going up, which is what we expected. The software here is pretty sensitive to the motion that you give the man with your finger on the mouse pad. You can see it's quite jumpy. It is hard to drag the man across at a constant velocity, but on average, I'm giving him about a 5 meter per second velocity, and so you see something that's quite similar to what we saw over here. And I'm going to ask you to keep going back and forth to this simulation to try different things and really get a feel for what's going on. One other thing you can do, click playback, slow down the playback, and then click play, here we go. You're going to get to watch what happens. As he starts moving, there's his velocity vector pointing to the right. You see I'm struggling to keep it constant. I'm doing a so-so job, and that's why I'm getting the jumpy velocity graph. However, it does work. It does give the motion that we described, right? Position going up. All right. Anyway, you can play more with that later. When you're done, you click Reset All. Yes, get rid of the acceleration graph, and you're ready to start a new one. Okay? Let's take a look at a slightly more complicated kind of motion. These images again out of Physics 11, this time for acceleration, for speeding up. So I'd like you to take a look at the caption for the first graph, the position time graph for a hawk that has a constant positive acceleration. You know from a position time graph that if there's a curve, the velocity is changing. If it's curving up like this, the velocity is increasing. The object is speeding up. Now, if I were to ask you to make a velocity graph from this, how would you do it? Would you measure the positions and divide by the times? If you did, you'd be making a mistake. You'd be calculating average velocities. What I want on a velocity time graph are instantaneous velocities every second, for example, at 1, 2, 3, 4, and 5 seconds. How could you know what exactly is the velocity at each of those seconds? Do you remember on a position time graph, the instantaneous velocity is given by the slope, but the slope of what? The slope of a tangent is the answer. So what I've done for this graph is I've added in the grid lines. They're missing from your textbook, but you can try this if you don't draw in your textbook, please, but trace it out on a sheet of paper and give it a shot. What we're going to do is get some straight lines going here. I'm going to measure some tangent slopes. I'll do my best here. As you know, it's not easy to make tangent slopes in this program that I'm using, but there's a tangent to the point time equals 1. Measure that tangent slope. Maybe you'd pick this point, and maybe you would pick that point down there. You could say something like slope equals y2 minus y1 over x2 minus x1. And let's see, what do we get here? The y2 value is 10. The y1 value is 0. The x2 value is 4. And the x1 value is maybe a half, something like that. So I'd be doing approximately, remember these are just approximate numbers, 10 divided by 3.5, which is approximately equal to 3. I'm not going to bother with a calculator because the point is just to get an idea of how they produced the velocity graph. They said 4. Okay, well maybe I didn't do a very good job of drawing my tangent. But my point is, if you did tangents at all these different points, you could construct a velocity graph. And it looks like what they're showing us is that the velocity is increasing at a steady rate. The hawk goes from 0 to 4 meters per second in the first second. Then it goes up another 4 meters per second in the next second. Then it goes up another 4 meters per second in the next second. This is what we call uniform or constant acceleration. And that's what happens when the velocity number changes at a steady rate. Notice how the slope of the line is constant. That should not surprise you because as we discussed on the previous slide, if you have a constant acceleration, you'll have a constant slope because slope is the same as acceleration on this kind of graph. In fact, what is the slope? If we do the rise over run over here, we're going to get the acceleration. Well, for a straight line, I can pick any 2 points on the line, so let me make my life easy. 0, 0, and what's this going to be? 5, 20. So I've got a rise of 20. I've got a run of 5. That's going to give me 4. The units are meters per second down. That's from this. And in the denominator, they are, of course, seconds. That's from this. So this will give me 4 meters per second, or 4 meters per second squared, letter D for down in square brackets. And so that's my acceleration. Once again, I can calculate the area beneath this graph, and I'll leave it to you, because I've run out of space here. Find the area that is covered by this triangular shape, which looks roughly like that. Find that area, and see what you get. Remember, the area of a triangle is a half base times height. The area should be, so I'm asking you to check on your own, it should be the displacement. How are you going to check this? Well, look back at your position graph and see whether the displacement of the hawk in those 5 seconds is the same as the area on the graph. Just a word of warning, this graph goes up to 6 seconds, but this one only goes to 5. So since you're calculating area up till 5, you'll want to look at the position after 5 seconds and see whether you get the same number. Check that out. All right. Moving along further, we're going to use the fact of the day, the fact about slopes and the fact about area, to calculate some of the information from the velocity time graph here. So here's a graph also out of your book, and it shows three intervals. Interval AB, where an object appears to be gaining more and more velocity as time goes by. Interval BC, where the object seems to move at a steady velocity of about 14 meters per second. And then interval CD, where the object seems to be going from 14 meters per second to 12, 10, 8, slowing down to a stop. So the first thing I'd like you to do is just try to describe in words what's going on using words like speeding up, slowing down, etc. So take a moment, pause the video, and see if you can make a description of what's going on here. Okay, and you're back. The second thing I'd like you to do is to use some of the slope ideas to find the acceleration. So for example, in the interval AB, what you can do is find the slope. And you could call this AB, finding the slope. This, of course, will be a rise divided by a run. And therefore, you're going to calculate the acceleration. So make a list of the accelerations that you get for AB, do it again for BC, and do it again for CD. The third thing I'd like you to do is to calculate the areas, which, as we've mentioned, are displacements. And once again, I'll do this in a different color so it's a little easier for you to see. Find the area in AB, that'll be triangular. Find the area, oops, not drawing too straight there. Find the area in BC, which will be rectangular, and then find the area in CD, which once again is rectangular, and see what you get for the displacements in each area. And then I'd like you to use that to find the total displacement. Once you have all 3 displacements, you can add those up and see what the total is. So this would be a good exercise for you to try just to get used to using those facts of the day, the slope and area idea of a VT graph. And so at this point, let's just pause for a moment and think about these graphs. They're quite powerful in the sense that you can get pretty much all the information about an object right off of the graph. You can either read it directly, getting the velocity, or you can do a slope to get the acceleration, or you can do a displacement, an area calculation to get the displacement. That's why these graphs are the ones that you're going to see we use the most in this course. All right, moving on. Next up, I want to give you a more challenging velocity graph, and I'd like you to do pretty much what you did back here, where I asked you to describe in words what's going on, find the slope, and find the areas. Do that for this graph. However, can you see with this graph, something is happening that didn't happen on any previous graph. See if you can pause the video and find out what that is. Okay, and you're back. What is it? Well, let's follow the graph. It goes up, the velocity is increasing. You might notice that in the beginning, the velocity is not 0 like it was in every other example. Does the velocity always have to be 0 in the beginning? No, you could be observing something that's already moving once you start timing it. The velocity increases, we've seen that before, it increases at a steady rate, and of course that means there's an acceleration. So you can find the acceleration information off of this by calculating the slope. Then the object stops accelerating, it moves at a steady rate of 15 meters per second for a little while, and then the velocity diminishes. The velocity becomes less and less until we get to a zero velocity, which means we're stopped. And then we stay at a stationary state for a few seconds, only to pick up the pace now. But look what's happening. Here's where things get different. We're moving into the negative velocity region. What does this mean? What is a negative velocity? Well, if you look at the graph, you'll see it's a negative velocity to the east. Think back in class. What do negative velocities east mean? They're the same as positive velocities to the west. And so what's really going on here is the object which was stopped in interval D is now going negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters per second east, or positive 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters to the west, which means the object in E is actually picking up speed, but in the opposite direction it was going to begin with. In other words, the object has turned around and is now heading back to wherever it came from. Eventually it achieves a constant westward velocity of about 10 meters per second. So here is a description of what's going on. And next up is, can you use your position information? So here we're talking about using the area ideas. Could you use the area ideas that we've learned on this graph to make a position graph? In other words, use this graph to sketch an entirely different graph. And can you then do the following? Figure out what's going on in terms of the acceleration on this graph. So in other words, calculate slopes of each of the segments A, B, C, D, and E. And then what I'd like you to try is finally to make our third graph, which I have not mentioned yet in this class, the acceleration time graph. What is an acceleration time graph? Well, as its name suggests, what you're going to do here is you're going to use all the accelerations, which of course are slopes, and you're going to plot, instead of velocity versus time, you're going to plot acceleration versus time. Okay? So at this point, I think you should pause the video, and for each of the lettered intervals, take a moment to see what you would get for all of those different positions via displacement and the accelerations via slope. I'm going to pause the video and do the same, and then we'll compare answers. Okay folks, hi, I'm back. I've done my calculations and I've decided to display everything for you so that you can follow along and see exactly what was going on. What I did was I cut and paste so that I made a little bit of space, and I color-coded all of the areas and slopes that I was going to calculate. Let me explain. In part A here, I have designated the calculation area to be over here in green, and I show you the slope calculation. So the slope calculation, y2 minus y1 over x2 minus x1, we're going from this point here, 0, 5, up to this point here, 4, 15. By the way, if you have trouble guessing what the numbers are, I've written them in along the horizontal axis for you. y2 minus y1 over x2 minus x1 gives us 10 over 4, which is 2.5. So this represents a slope and acceleration going to the east, and that's written in here. Now the area may have tricked you if you tried this on your own and now you're comparing with my calculations. The area includes all of the area between the graph and the time axis. So there's actually a triangular area and a rectangular area. I've drawn these out. They are a base of 4, and the rectangle has a height of 5, as you see here, but the triangle has a height of 10, going from 5 up to 15. So I've drawn these in down here, and I've shown you a half base times height, length times width, subbed in my numbers. I get an answer of 40, which means the displacement in interval A is 40 meters to the east. And basically I went through all of the other intervals doing the same thing. Some are easy, some are not so easy. Part B is very easy. The slope of the line, horizontal, that's a slope of 0. I'm not going to show you the calculation, that's easy enough. The area is a rectangle with a height of 15 and a base of 2. 15 times 2 is 30. I'm not going to show you that calculation, it's easy enough. In part C, Now let's do the slope. We have a negative slope here, so I'm going to show you this calculation because here's a little twist, a negative slope. y2 minus y1 over x2 minus x1. We're starting over here at 6, 15, and we're ending up here at 12, 0. Here's y2 minus y1 over x2 minus x1 for a slope of negative 2.5. That's going to be your acceleration. The area here, a triangle, easy to calculate. Go ahead and do that yourself. I get 45. In part D, very easy. There's no slope, it's 0, and there's no area because the line is right along the time axis, so that's shown over here. In E, we now have another twist. While the slope is negative, and that's easy enough to see, here's your slope calculation, by the way, the area is now below the time axis, and in physics, that represents what's called a negative area. Now, you can't go and buy a house with a negative number of square feet in terms of its area. You can't go build some furniture out of wood and go to the lumber yard and order a certain number of negative square meters of wood. That doesn't make any sense. But remember, area on these graphs is not the same as area in regular everyday life, so we can have negatives. Since area is displacement, this means that the object is actually going in the negative direction. And remember, when we analyzed the motion of an object whose velocity graph has dipped into the negative, we did discuss earlier that that means the object has turned around. So it's coming back, which means it is chipping away at its position. It is coming back to the origin. That's why we have a negative area for E. Finally, in F, which is coded blue, we have a slope of 0, once again, a horizontal line, and again a negative area. We're still heading back toward the origin, negative 20. So now what I'd like you to do is first of all, check your calculations and make sure you are able to do these same ones. If you have mistakes, go back and fix them. Pause the video if you need to do that. Or if you have these, now the next thing to do is to turn these into a graph of position versus time and a graph of acceleration versus time. So you're going to be plotting all of your areas against time and your slopes against time. So what you can do is set up a couple of blank graphs that look like this, a position time graph showing all the important times along the time axis, such as you saw here. Those important times are 0, 4, 6, 12, 14, 18, and 20. So I've got those over here. And do the same for an acceleration graph with those important times where the intervals start and end. As far as the vertical axis goes, how does that work? Let's look at acceleration for a moment. You see I've put in 2.5 and negative 2.5. Why did I do that? Well, if I look at all of the slopes that I had 2.5 positive, 0, 0, negative 2.5, 0, and negative 2.5. Why are they all either 0 or negative 2.5? Well, that's a bit of a coincidence. I didn't mean to make them all 2.5 or negative 2.5. However, since those are the extremes, that's what I'm going to be plotting here, so I put in these important points. Let's sneak a peek at the position graph. You'll notice 40, 70, and 115. What are these? I don't remember seeing a 70 or a 115 in the area calculation. Let's look back here. I see a 40, I see a 30, I see a 45, a 0, a negative 20, and a negative 20. You might be wondering, why are the negative 20s not present in here? Why are there 70s and 115s plotted here? The answer is as follows. In the first section, A, we went 40 meters east. That was the displacement. In the next section, B, we went 30 meters east. However, this 30 meters east is in addition to the 40 that we had already gone. So you got to take this 30 and you have to add onto the 40. That's going to give you 70, and that's why you see a 70 here. Where does the 115 come from? Same idea. At this point in part C, we added 45. What did we add 45 onto? We added 45 onto the 30 and the 40 that we had already done. 45 plus 30 plus 40 is 115, and that's why here you see that number. So what do we do now? Now we've got to form the graph. And here's where you got to think about shapes. For example, what's going on in A? Here's where your word description comes in handy. Did you describe the motion of the car using words? Well, if you didn't, go do that now because you're going to need it. Here we have a car that is speeding up. So you think to yourself, it's speeding up, the displacement is 40. What does speeding up look like on a position graph? So in green, what does 40 look like? Well, if we assume the initial position is 0, the reference point, then you go from 0 to 40 meters at a time of 4 seconds. Speeding up would be a curve upward like that. If you didn't use a word description, you might not know that you need to use a curve here. And you know what? I'm going to just exaggerate that curve to really impress upon you that these word descriptions are important. I don't even like that curve. Let's see, I've got to work on my art skills here. Okay, well, that'll have to do. Let's go back once again. What happened in part B? We moved at a constant speed. So what's that going to be on your position graph? It'll be a straight line for an additional 30 meters. Straight line this time for another 30 meters. That gets me to the 70. See, is that a good straight line? I could do better. Why don't I just add a straight line there? Like that. There we go. Next interval is the magenta interval. So I'm going to select the color magenta. And now what am I doing here? This is a velocity that is becoming less. 15, 10, 5, 0. I'm slowing down, and I'm going 45 meters additionally, 45 more meters as I slow. What does it look like to slow down and go 45 more meters? Well, it's going to get me to 115, and if you remember, whoops, not a very good curve there, but if you remember when we studied velocity graphs, position graphs, a curve like this shows slowing down. What happens next? I stop for 2 seconds. That's D. What does a stop look like? Well, in a position graph, a stop looks like a horizontal line. So for 2 seconds, I am stuck at the same position. I don't move. My position stays steady, horizontal line. Now what happens? I start going the other way, and my velocity goes from 0 to 5 to 10. I'm speeding up. Again, you need those words in there. You got to make a word description of what's going on. I'm speeding up going west. How do I show speeding up going west and covering, by the way, 20 meters? Here's what it looks like. Speeding up would mean that first of all, for 20 meters is going to get me from 115 down to 95. So I've got to be prepared to draw a 95 right about there. And I've got to show that my velocity is getting more and more. And the way you do that is by showing a line that starts to slope steeper and steeper. Because if you remember, slopes of tangents show velocities. An ever steepening curve means I'm picking up speed. And finally, in the very last interval, I go at a steady rate for 2 seconds. I go 20 more meters at a constant velocity of 10. And so what's that going to look like? It's going to be the following. Sorry, what color did I use there? I used blue. Okay. So in blue, for 20 more meters, meaning I'm going to get from 95 down to 75. And where's that going to bring me? Somewhere along here. I'm going to have a straight line for constant velocity, and that is your position time graph. I bet you didn't get the whole thing right if you tried it before you listened to how I did it. And that's okay. Mistakes are what we make before the test so that we can find out the right way to do it. This stuff is tricky. You got to try it again if you didn't get it the first time. Rewind the video and give it a listen. All right? Let's take a look at the acceleration graph. I think you'll find this one quite a bit simpler. Let's look at our slopes. A slope of 2.5, a steady slope of 2.5 lasting for 4 seconds in green. Here we go. A steady slope would translate into a steady value of 2.5 lasting for 4 seconds. Now what happens? We flatten out. 0 slope, no acceleration. In orange, no acceleration lasting 2 seconds. Here it is. Down there. What happens next? We now have a negative slope, magenta color, lasting 6 seconds, negative 2.5 steady. So down here like that. And then we have no slope, 0 acceleration, lasting 2 seconds. Color is black. So for 2 seconds, oops, that's not a very good line there. There we go. And by the way, it looks like I forgot to put in the 14 there. There we go. And finally, or rather almost finally, red, negative slope 2.5, lasting 4 seconds. Negative slope 2.5, lasting those 4 seconds. And finally, 0 slope lasting 2 seconds, blue. Okay, and there you go. There is your acceleration graph. It's a rather jumpy acceleration. It jumps from 2.5 down to 0, and then from 0 down to negative 2.5, then back to 0, then back to negative 2.5, and back to 0. So this is not a very realistic kind of motion. Usually accelerations are a little smoother. In fact, I would describe this acceleration as very jumpy, or actually what physicists call it is jerky. In fact, the acceleration's rate of change is called the jerk. And so there's an interesting fact for you. The jerk would be the rate of change of acceleration, and it is measured in, believe it or not, meters per second squared per second, or meters per second cubed. There is actually a unit of measurement called that, and it's known as the jerk. However, in grade 11 and 12 physics, we don't really talk about this, so this is nice to know, so you can impress your university professor that you know this, but we aren't really going to talk about it, so don't sweat it. All right, there are your graphs, and therefore I get to the final topic that I'd like to discuss, which is I want you to get more practice taking, let's say, a velocity graph that has no numbers, just shapes, and using it to sketch the position graph, and also using it to sketch the acceleration graph. Let's just do one really, really quickly here. If you found this exercise here between this and that, if you found this pretty agreeable with you and you were able to understand it after a little bit of struggling with it, then I think you'll find this not too much harder. The only weird thing here is that they don't give you any numbers, so here's what they're asking you to do. Take the velocity graph and make a position graph. How would you do that? Well, remember, these are areas. It's an area idea, and it's also a shape idea. Like in part A, we have a constant velocity going for a certain area that we don't know. So what do we do here? Well, we just draw constant velocity. That's a straight line moving away from the origin. Now we're speeding up here as we move further from the origin because we're putting on more area. So how do I show that? Well, you show speeding up with a curve like that. What happens in part C here? Well, now you move at a constant velocity yet again, an even higher velocity. So show me a steeper line than before, which is straight. And so now you're getting up here. Now we slow down until we reach a velocity of 0. So show me slowing down until you stop. Well, here's what slowing down looks like until you level off at a stop, horizontal line, 0. Now you stay where you are for a certain amount of time. That'll be a horizontal line like this on a position graph. And now I see I got to get rid of this, this circle here, or this arrow. There we go. What happens now? You come back to the origin speeding up. So what does that look like? Well, you got to show me returning to the origin would be coming back this way, and you've got to show me speeding up, which means slopes that get steeper. So how is that going to look? Just like going over a ski hill, it'll be like that. Until you reach a constant velocity that is taking you back toward the origin. A constant velocity is a straight line, and so now you're going to show me something like that. And these are your intervals, A, B, C, D, E, F, and G. Okay? So we've sketched the position graph based on the shape of the velocity graph. No numbers involved, just shapes. How would you do the acceleration graph? Usually this is a bit easier. So now make this transition. What do we got here? Constant velocity, that's zero acceleration. Since I'm going to be on the axis here, I'm going to use a different color to show you a zero acceleration. Now I've got a positive acceleration that is steady. It's a constant slope. So I have a steady value of acceleration like that. Now I'm stopped. Sorry, I'm not stopped. I'm moving at a constant velocity. Zero acceleration in C. Show me zero acceleration. That would be an A value of 0. Now show me a negative acceleration because the slope becomes negative. So that'll be down here. Once again, zero acceleration, zero slope. In fact, you're stopped. So that's going to look like this again. In F, a negative acceleration again, although the slope here is much less negative than it is here, so don't show me so much negativity. Show me that, not as negative as this one. And finally, a zero slope again, and so show me a zero acceleration. Here's your acceleration time graph that corresponds to this. A, B, C, D, E, F, and G. I know my alphabet. Woohoo. Okay, folks, that's it. I know it's a long lesson, however, there is a lot of stuff to be covered. One last thing, if you find yourself doing well on this, or if you find you want a slightly different perspective, I'm inviting my grade 11s to take a look at a grade 12 video that I did on this topic. This is the one. It's position, velocity, and acceleration graphs all wrapped into one. It says grade 12 physics. You could watch this if A, you want more practice, B, you want a slightly different perspective, C, you are having trouble falling asleep and want to listen to really boring videos. All right, there's a jibe against myself. That's fine. I can live with it. Thanks for watching and have a great day. See you in class.